Le Chatelier's principle. Le Chatelier's principle is one of the most important qualitative ideas in chemistry. It is a way of talking about the effect of changes on an equilibrium system that does not require calculations. Le Chatelier's principle states, if a stress is applied to a system at equilibrium, the system will shift its equilibrium position so as to counteract the effect of the stress. There are several key parts of this principle. Number one, the system must already be at equilibrium. If not, then the principle technically does not apply. Although chemists will sometimes use the principle in non-equilibrium systems, it is not technically valid under those circumstances. 2. Stress is a change that is introduced into the equilibrium by an experimenter or by a natural change in the outside conditions. This causes the system to no longer be in equilibrium. 3. The system then shifts in order to re-establish equilibrium. This shift means that either A. Some reactants are used to make more products, or B. Some products are used to make more reactants. So either A. There are more products and fewer reactants than before the shift, or B. There are more reactants and fewer products than before the shift. This is what a shift is. Either there are more products after the shift, or there are more reactants after the shift. Number 4. The shift is such that it counteracts the stress. That is, whatever was done to the system tries to undo. But what is a stress? A stress is a change in A. The concentration of an individual reactant or product, B. The temperature of the system, or C. A change in the overall volume of the system which causes a change in the pressure of the system. While the equilibrium will shift to counteract the stress, it almost never completely counteracts the stress. So, for example, if energy is added, perhaps to try to raise the temperature, then the equilibrium will shift to try to absorb the added energy. But not all of the energy will be absorbed, so the temperature will still increase, but not as much as expected. Or if the stress is that the concentration of A is increased, then when the system reaches equilibrium again, some but not all of the added A will have been reacted. Or if the pressure has been increased by lowering the volume, then when the equilibrium is reestablished, the pressure will have decreased again, but not back to what it was before the change. Note that the shift will change the concentrations of all reactants and products. The reason for this is that the only way the system can shift is to either use up reactants to make products, or to use up products to make reactants. A shift to the right will cause all product amounts to increase and all reactant amounts to decrease. A shift to the left will cause all reactant amounts to increase and all product amounts to decrease. Let's look at each of these stresses a little more closely. The effect of changing the concentration. If we change the amount of one reactant or product so that the equilibrium is thrown off, then, when we reestablish equilibrium, the amounts of all the reactants and products will have changed. Let's look at one example of this. The Haber process was developed by the German chemist Fritz Haber in 1909. It is used to produce fixed nitrogen, that is, nitrogen in a compound, from the nitrogen in the air. In this process, nitrogen from the air and hydrogen gas react together to form ammonia, NH3. This is used for the production of fertilizers today, and was initially used for the production of explosives during World War I and World War II. We start with the system at equilibrium, and at some point we add some additional hydrogen. The system reestablishes equilibrium by decreasing the amounts of H2 and N2 and producing more NH3. Note that once we are at equilibrium again, there is less N2 than we had to begin with and more NH3 than we had to begin with. For the H2, the substance we changed, there is more than we had to begin with, that is, before we added any, but less than the total of what we started with plus what we added. If we increase the amount of H2, then the equilibrium will shift to reduce the amount of H2 by reacting it with N2 to form NH3. On the other hand, if we decrease the amount of H2, then the equilibrium will shift to make more by decomposing NH3 into N2 and H2. Adding H2 causes the equilibrium to shift to produce more NH3. That is, it shifts to the right. Decreasing the amount of H2 will cause the equilibrium to shift to produce more H2. That is, it shifts to the left. In general, the system shifts away from what is added and toward what is taken away. In the industrial process, where we want to make more NH3, one of the things that is done is to remove the NH3 that is produced by getting it to condense into a liquid. This helps push the equilibrium to the right. The effect of changes in temperature. Cobalt-2 ions form complexes that have different colors. With water it forms a pink complex, and with chloride it forms a blue complex. The equilibrium reaction between these two complexes is given on this slide. Increasing the temperature will cause the equilibrium to shift to the right. We increase the temperature by adding energy. Since the reaction is endothermic, increasing the temperature will cause the equilibrium to shift to absorb heat, which happens when the forward or endothermic reaction occurs. Decreasing the temperature will cause the equilibrium to shift to give off heat, which is to the left. Here are pictures that show the solution at room temperature, the left picture, which is purplish. At warmer temperatures, the middle picture, the color is more blue. And at colder temperatures, the right picture, the color is pink. The effect of changes in pressure. When there are gases present in the equilibrium system, changing the pressure may affect the equilibrium. This is the most complicated of the three stresses to deal with. For example, take this equilibrium, in which 2 hydrogen ions and 1 carbonate ion are in equilibrium with liquid water and carbon dioxide gas. Changing the pressure of any gas will change its concentration. So if we increase the pressure of CO2, the concentration of CO2 will also increase. If there is only one gas present, then we can treat changing the pressure like changing the concentration of that substance. So increasing the pressure will cause this equilibrium to shift to the left. However, if more than one gas is present, then changing the pressure by changing the volume of the container will change the concentration of all the gases in the system. This is a much more interesting situation. Consider, for example, the water reaction. 2H2 gas plus O2 gas in equilibrium with 2H2O gas plus heat. If we decrease the volume of the container, then the partial pressure of each gas will increase. How will that affect the equilibrium? In the language of the stresses, if we increase the pressure in the container, the equilibrium will try to reduce the pressure. According to the ideal gas law, there are 3 ways the equilibrium can affect the pressure in the container. It can try to 1. Change the volume. 2. Change the temperature. Or 3. Change the number of moles of the gas. We are in control of the volume of the container, so that leaves the equilibrium only changing the temperature of the system by releasing or absorbing energy, or changing the number of moles of the gas by changing the amounts of products and reactants. The only effective way for the system to affect the pressure is to change the number of moles of gas. Here's our reaction again. We have increased the pressure, so the equilibrium will try to decrease the pressure by reducing the number of molecules. There are 3 molecules in the reactants, 2 hydrogen molecules and 1 oxygen molecule, and only 2 molecules, both water, in the products. So by taking reactants and making products, the number of gas molecules will be decreased. Shifting the equilibrium to the right will decrease the pressure because there are fewer gas molecules, and shifting the equilibrium to the left will increase the pressure because there will be more gas molecules. Here's another equilibrium, H2 gas plus Cl2 gas in equilibrium with 2 HCl gas. What happens to this equilibrium when we increase the pressure by decreasing the volume of the container? In this reaction, there are 2 moles of gas in the reactants and 2 moles of gas in the products. So no matter which way the equilibrium shifts, the number of moles of gas does not change. Since shifting the equilibrium will not affect the number of moles of gas, the equilibrium cannot shift to reduce the pressure. So changing the pressure by changing the volume will not affect the equilibrium. To summarize the pressure effects, changes in pressure by changing the volume of the system will affect the equilibrium if there are gases involved in the equilibrium and there are different numbers of moles of gas in the reactants than in the products. Increasing the pressure by decreasing the volume will cause the equilibrium to shift away from the side with more gas molecules. You may wonder why catalysts do not have an effect on the equilibrium. First of all, adding a catalyst will increase the rates of both the forward and reverse reactions equally. But in addition, adding a catalyst has at most a minimum effect on the concentrations of the reactants and products. Remember that the mechanism does not impact the equilibrium expression, so changing the mechanism, which we do when we add a catalyst, has no impact on the equilibrium. However, we will get to equilibrium faster. But once we are at equilibrium, the position of the equilibrium, the amounts of reactants and products present, will not be affected by the addition of a catalyst.